Thank you. Good afternoon, everyone. Today, I want to share you with our work on detecting sensitive user inputs in mobile apps. And this is a joint work with the guys in NEC Labs and Georgia Tech. Nowadays, smartphone and mobile apps have been an essential part of our lives. And at the meantime, the user's privacy has become a serious concern. And it's common for the apps to disclose the sensitive data to local storages, to logs, or to some public external channels like internet. But unfortunately, such disclosures can be hijacked or maliciously retrieved by adversaries. And this can lead to some serious leakage of users' privacy. Actually, there are a lot of existing efforts working on this area, but their focus is mainly on the sensitive data defined by certain APIs. For example, the APIs that can return the device identifier or the phone's current location. And most of these data are permission protected. Together with the cache tag in previous talk and the UI peak in next talk, actually our work is among the first to detect user inputs as sensitive sources in mobile apps. And user inputs in mobile apps is quite common, and none of them are permission protected. Then we need to understand the context of the inputs to determine whether they are sensitive or insensitive. For example, an input of credit card is sensitive, but the comment for an app is insensitive. For sensitive user inputs, the data can be retrieved in the code like this and later be disclosed to some public channels like internet. For the insensitive user inputs, the data flow actually is the same as that of sensitive user inputs. Then if we want to do some disclosure analysis, we cannot simply discover the sensitive sources in the code by only analyzing the code. In fact, if we want to do some such code analysis, we confront several challenges. How to systematically discover the input fields from app's UI, and how to identify which input fields are sensitive, and also how to associate the sensitive input fields to the corresponding variables in the apps that store their values. And the second one is the key problem in our work. We come up with an intuition that a user can simply distinguish the sensitive input fields from the insensitive input fields. Then, if we can mimic how a user looks at the UIs, we can also discover the sensitive input fields. Fortunately, we are able to statically build the UI via certain technologies. Mobile platforms provide some kind of static layout formats for the developers to create the UIs. And the rapid development toolkits provide what you see is what you get, editing features to render the layouts. And the rendered UIs are close to what you see on the smartphone screens. Then with the rendered UIs, we can devise some techniques to associate the text labels to the input fields, and then such that we can mimic from the user's perspective. Then based on the intuition, we propose SUPOR, which is a precise and scalable approach to detecting sensitive user inputs in mobile apps. Before we go into the details, I want to quickly introduce some terminologies. As in this example, we can find the text labels, the input fields, and the hints for the input fields. The text labels and the input fields are called UI widgets, and they may be referred in later talk. The layout files contain the definitions of the UI widgets, as well as certain attributes. For example, the identifier of the widget is defined here, such that the developers can reference the widget in the code. And some interesting attributes can indicate the expected type of inputs. Okay, then we come to the whole view of SUPOR. SUPOR takes an input of a mobile app and outputs the bindings of the sensitive user inputs and the variables in the code to enable some further analysis. SUPOR itself consists of 3 steps. The first step is to analyze the statically defined layouts, which include the static parsing and the rendering. Then SUPOR wants to determine the sensitiveness of the input fields via some techniques. And at the end, it binds the discovered sensitive user inputs to the variables in the code. At the very beginning, we want to know that which layout files contains input fields, because we don't want to spend efforts on those files that do not contain any input fields. Then with these initial discoveries, SUPOR can statically render the layout files to some UIs, and these UIs are nearly the same to what you see on the smartphone screens. For example, by rendering layout A, we can get this, and by rendering layout B, we can get this. With these rendered UIs, SUPOR can extract important information for subsequent use. For example, for the marked area, SUPOR can extract information like the text, the hint, and also the coordinates. The coordinates are used to associate the text labels to the input fields. Then, with all the information we've gotten, SUPOR tries to determine if the input field contains sensitive data. It performs a 3-step sensitiveness analysis. At first, it tries to check whether the UI wedges contain some attributes that can indicate the sensitiveness of the data. This is an example of a sensitive input field. But if the sensitiveness cannot be determined, SUPOR inspects the input hints of the input field. In some apps, the users are prompted to enter password, and in our previous example, the hints tell the user how to enter the data. If the hint contains sensitive keyword, then the field is sensitive. If not, SUPOR wants to check whether the associated text label contains sensitive keywords. In our previous examples, the label comment indicates an insensitive input field, but labels card number and expiration date indicates sensitive input fields. The first 2 steps are simple, but here comes to a challenge that how to precisely associate the correlated text label to a given input field for the 3rd step. An intuition is that labels at different positions relative to the input field have different probabilities to be correlated. Here are some examples. The text label can be at the left of the input field, at the right of the input field. It can also be at above it or below it. And then we can assign some position-based weight values to the labels at different locations. And also, we see that the smaller the weight, the closer the correlation. Actually, we partition the UI plane into line parts based on the borders of the input field. And based on our observations for top-down and left-right layouts, the labels at left or above the input field are most possible to be correlated, while the labels at the right bottom corner are most impossible. To show how the text labels are associated with the input fields, we propose a geometry-based correlation score computation. For an input field and a text label with known coordinates, we compute a correlation score for each pixel in a text label. And this computation actually takes into account both the distance and the position-based weight. Then later, an average score of the correlation score is computed for the text label. And usually, an input field may have more than one alternative labels. Then SUPOR selects the one with the smallest correlation score. In this example, both the input fields, a card number and the expiration date, have 3 alternatives. And the correlation scores are shown here. Based on our policy, the label card number is associated with the number field, and the label expiration date is associated with the date field. Now we have all the label text for each input field. We want to determine whether these input fields can contain sensitive data. We propose a keyword matching approach with a predefined sensitive keyword dataset. In our previous examples, card number and the expiration date matches some predefined sensitive keywords, and those 2 input fields are sensitive. But comment doesn't match any sensitive keywords, then the corresponding input field is insensitive. You may want to ask why the keyword matching approach is effective. One important reason is that smartphone screen is relatively small, and the phrases or sentences are short. And we only analyze the most relevant text label for each input field instead of analyzing a lot of labels. After determining which input fields are sensitive, we want to bind the discovered sensitive user inputs to the variables in the code to enable some further analysis. And the identifier of the widgets are referenced in the code. Then this can help SUPOR to bind the variables. But one problem is that different layout files may contain input fields with the same identifier. And some are sensitive while the others are insensitive. Like in this example, input 1 for the credit card number is sensitive, but it is insensitive for the search keywords. If we just simply bind the identifier input 1 to the references in the code, we cannot distinguish the references to sensitive user inputs from the insensitive ones. We solve this problem by leveraging a backward slicing. Like here, input 1 can be either sensitive or insensitive, and we can find out the references in the code. Then for the first reference, we can obtain the backward slice like this, and by further checking the slice, we can confirm that input 1 here is associated with the widget defined in layout binding information instead of layout search. Then SUPOR can mark the corresponding variable text input 1 as sensitive. Then for the second reference, a similar slice is found here, and actually the input 1 here is associated with the widget defined in layout search, which actually finally indicates an insensitive input field. Here I finished the talk for the design part, and next I want to discuss some implementation and evaluations. We built SUPOR only for Android apps, while the idea is quite general for the other platforms, and it is built on some existing tools. And we limit the type of input fields for a small set of user inputs in Android apps. Some other user inputs are ignored, like the checkbox. And we also implemented a sensitive user inputs disclosure detection system to demonstrate the usefulness of SUPOR. And the tool is evaluated on 16,000 apps. The UI Sensitiveness Analysis, including rendering all the layouts in one app, is quite efficient. Actually, more than 96% of the apps require less than 10 seconds. And the average analysis time is only 5.7 seconds for one app. We manually examined 40 apps, which has 485 input fields. And we use recall and precision to describe the accuracy. Both of them are 97.3%, which means that we have a low false positive rate and low false negative rate. One cause for the false positives and false negatives is that SUPOR does not have sufficient context to identify sensitive keywords. For example, security answer is a predefined sensitive keyword, but some apps only use answer in the UI, which is equal to security answer within that context. But answer itself is too general, and SUPOR doesn't consider it as a sensitive keyword for reducing false positives. But this sometimes cause false negatives. Then in some other cases, hate of a human being is sensitive, but hate of an image file is insensitive. SUPOR considers hate as a sensitive keyword. Then this can sometimes cause false positives. In addition to this keyword part, SUPOR sometimes incorrectly associates the text labels to the input fields. Like in this example, the long sentence is actually a supplemental description of the email field. But when SUPOR doesn't determine the sensitiveness of the delivered instruction field, it tries to find a label. And this happens to be this description for the email field. And the label contains sensitive keywords. Then SUPOR marks the delivery instruction as sensitive. This is actually a false positive. For the sensitive user inputs disclosure evaluation part, the whole throughput is about 11 apps per minute on a cluster of 80 servers with 3 apps analyzed on each server in parallel. And we manually checked 104 apps. The false positive rate is 8.7%. In addition to the errors of identifying sensitive user inputs, the limitation of underlying taint analysis framework is the major cause for the false positives. If you want to know some detailed data, please refer to our paper. And here are some real cases. In the first one, the weight, the height, and the age of the human beings are identified as sensitive. And in the second one, the credit card number and the security number and the holder's name are identified sensitive, and they are discovered to be disclosed to public channels like internet or login. In these apps, the data flows are somehow like this, but the existing approach neglects the sensitive sources of user inputs, so they cannot detect the sensitive data disclosures in these examples. But SUPOR can identify the sensitive sources in the code and thus discover these disclosures. Okay, let me conclude our work. We started the possibility of detecting sensitive user inputs, which is important, but mostly neglected sensitive sources in mobile apps. And we proposed SUPOR, which has a high recall and precision rates. SUPOR mimics from the user's perspective by statically rendering the layouts, and it leverages a geometry-based approach to associate text labels to input fields. And it uses some text analysis to determine the sensitiveness of the input fields. At the end, we also performed some sensitive user inputs disclosure analysis to demonstrate the usefulness of SUPOR, and the false positive rate is relatively low. Okay, that's all. Thank you. Any comments or questions?
Okay, so we have lots of time for questions. Please.
Okay. This is Haibo Chen from Shanghai Jianjun University. Very nice work and a nice talk. So my question is, do you assume that the apps we are using the standard UI component? How about like apps using some customized UI, like directly drawing some UI component from like the canvas component?
Yeah, sure. When you use some custom widgets, like you define some classes that can extend the text view or edit text, right? Mm-hmm. Then when we render the layout, we replace these custom widgets with the standard widgets. Like if you define my edit text, when I render the layout, I replace this my edit text with edit text. The results should be similar when you develop the app in something like Eclipse.
Okay, I see. Thank you.
First in University of Michigan. So I remember in Android the layout can change dynamically in runtime. So it can be just the hints, and also those it can be totally like different from the layout.xml and the dynamic render view. So have you guys considered this?
Currently, we only handle the statically defined layouts. Sometimes the layout it may only contain a linear layout, and all the internal elements are added dynamically. We cannot handle that part.
So have you guys think about using dynamic, like monkey, to trigger those UI and then to read the UI dynamically, so you can just get the just what the user can see in the screen. So you just pass those like OCR or something.
That's a good suggestion, and I think we can do that in the future. And if we can do some deeper static analysis, we can achieve some similar results as the dynamic analysis.
I see.
But we didn't do that.
Thanks.
Okay, I also have one question, and you talked about false positives.
Right.
But how about false negatives?
You mean the false negatives for the disclosure analysis part?
Yeah, and also for the identification of sensitive fields, for both things.
I talked about the false negatives for the sensitiveness analysis. But for the disclosure analysis, because we don't have an oracle for the apps, so we don't count the false negatives.
And disclosure must not be malicious in the sense that, let's say I have an app where I enter my password, and the password is then transmitted to the server such that I can authenticate. So would you flag this as a disclosure, or?
We call it disclosure because we don't exactly know whether these disclosures are bad or good. For example, you enter some user ID and password, and they transmit it to the web server. It can be blind to log in to use some functionalities. But we only check that if these sensitive data are sent out via some public channels.
Okay.
And actually, we checked that most of the apps transmitted the sensitive data just via plain text, via HTTP instead of HTTPS or SSL.
Okay, so if there are no more questions, let's thank the speaker, and then we have the